Hello. So, we've seen the sort of geometric goal, right, when it comes to approximating the area under a curve or the area of a sort of object with a curved side. But unfortunately, right, math class, we're going to have to actually dive into the mechanics. So the question is, how do we actually do this, right? I mean, we saw that the idea is to sort of have these rectangles approximate the size, but our goal isn't just to get any approximation, right? Our goal is to get some sort of good approximation, whatever that means, which again is something that we will sort of have to tackle what we mean by that. So we want some sort of good approximation of these curved edged things, right? This area under the curve, using this rectangle method as a substitute, right? Because we can't sort of evaluate it directly, but for some generic curve. So we're going to start with a concrete example and sort of move through that concrete example on how we would actually literally compute this thing, literally get exactly what our estimate would be using a couple ways of sort of doing the rectangle method, right? Depending on how we want to lay out the rectangles and things like that. Then we're going to take sort of a quick break. So I'll let you know when to sort of rest your brain for a few minutes. And then we're going to try to tackle the generic formula aspect. So as we move through this, we're going to start with sort of a grounding idea and then move forward into the more general sort of idea as we go along. Okay, so that's the goal for this particular video. So consider the following. So we have here a shape. Now, when we say things like any generic curve, that also includes non-curved curves, right? So this also includes things with straight lines. So in particular, I want to use sort of for the sake of teaching, right? For the sake of sort of helping you have something concrete to grab onto here, I'm using a shape that you can actually compute the area of, right? This is a nice triangle. We have formulas for triangles. You can get an exact area for this. So that'll give you sort of a benchmark to use when we approximate the area using our rectangle technique to see sort of how it works out, okay? So our goal here, even though we, again, to be clear, we could get an actual area for this thing using geometry, our goal here is to use the approximation methods, right? Which is laying sort of rectangles over these things, over this shape, and then using the area of the rectangles, adding them together to get some sort of estimate. But that means we have two questions, right? So firstly, how many rectangles do we want to use? And secondly, where should we put them? So again, for the sake of concrete example here, let's start with 3 rectangles. We're going to have 3 rectangles across this shape. Now the shape, right, has a total width of 6. So sort of an easy place to start would be to just make all these rectangles the same width. Now it turns out that doing that is actually going to be really helpful for a number of reasons. So this is something that we're always going to do. Strictly speaking, for this method, you don't have to do that. But if you don't make them all the same width, your brain is going to explode. So just always make them the same width. It is much better that way. So if we make them the same width, we have 6 width, right? We have 3 rectangles. So each of them has to be 2 units wide, right? 6 divided by 3. Okay. So that leaves us with, where are we putting the rectangles? How are we arranging these? So there's sort of an obvious starting spot, right? We could make the rectangles so that they sort of hit the curve, right? That diagonal line at one of the corners, right? So here we're hitting at the top right corner, right, for each of these things. And we sort of just make the rectangle based on that corner, right? So we know we want it to be the top right corner here. So this first rectangle, right, width of 2. It's going to hit on the top right-hand corner. So we have that dot, we have the base written out, and we just sort of extend to the left to make it a rectangle, right? And then we keep doing that. So the middle rectangle, right, is another width of 2. So it's between 2 and 4. Top right corner is over here. And then we sort of just go left and drop it down to make another rectangle. Same with the last one. So this is one way we could do this. But it's not the only way we could do this, right? So another option is we could do the same principle, but instead of taking the top right corner, we could take the top left corner, right? So here, right, if I want, say, the last rectangle, I could put the top left corner over here, right? I know it's going to hit, right? So the right-hand most rectangle, again, width of 2, so it's 4 to 6 is the x values down here. I go up until I hit, right, on the left-hand side, I go up until I hit the curve, then I just go to the right and drop it down, right? Now, I realize I said 3 rectangles, and there's only 2 here. But there is 3, it's just that one of them, that very first one, is sort of not really a rectangle, right? Because this curve, such as it is, goes down to the origin down here, right? So when I'm looking at the left-hand side, it goes up a height of 0 before it hits the curve. So this rectangle has a height of 0. And this is sort of important to keep in mind, is that when we talk about things like we're going to have 3 rectangles, or we're going to use 17 rectangles, or however many rectangles you want to use, these are sort of loosely right rectangles. Some of these, although they'll always have a positive width because we're doing that by making them all the same, right? So we carve it up. So it'll always have some nice width. Those heights could possibly be 0. So you might end up with sort of a empty rectangle, right? That doesn't really exist, but is there in the strictest sense. So this is a thing that can happen, and that's totally fine. Okay, it's part of the estimate process. All right, so we have the sort of right-hand corner, right, the top right, we have the top left. There is another one, though, which is maybe a little less obvious, but not unreasonable, which is that instead of picking a corner, we could take the middle, right? So instead of deciding, okay, I want to take where the right corner or the left corner meets, I could say, okay, I'm going to go where the middle meets, right? So again, if I look at the right-hand most rectangle, I know it's between 4 and 6, so I can go up the middle part, right, up along 5 until I hit the curve and make that the height, right? And I do that with all 3. So this is another way I could do this. So these sort of 3 ways represent the sort of 3 classic ways of arranging these rectangles, and they have not particularly original names, but again, math people like to name things in a way that make them easy to remember so that we don't have to remember stuff. So in particular, the one that uses the top right corner, that's called a right endpoint because we use the right-hand endpoint of that top as the sort of marker of where to make the rectangle. The one that used the top left, that's the left endpoint, again, because that's where we sort of use as the marker, the left side of that top. And the one that used the middle of the top line, that is the midpoint, right? So we use the midpoint of the top as the marker. So that's, I mean, they really are not cleverly named because we really just want to make them sort of easy to remember. Okay, so we've sort of talked about how to make sort of how many rectangles. We basically picked a number out of a hat. We're just going with 3 for right now for the sake of concrete values. We talked about the arrangement of these things, but what to do with these things, right? So there are some similarities between these things. So for example, for each of these, right, remember our goal is to write out the sum of the areas of these rectangles, which means ultimately we need to know what those areas are. But to get the area of a rectangle, you just need the width and the height, right? So area of a rectangle is width times height. Well, for all 3 of these, the widths are always the same, right? So really one of the things, and we'll sort of see this going forward, has come up a bunch of times, is really fundamentally the difference between these things is the height that's involved, okay? So stepping back a minute, our goal here, right, again, is to find the approximate area by adding up the areas of these shapes. So if I call, for any one of these, right, if I call the first rectangle R1, or the area of the first rectangle R1, the area of the second rectangle R2, the area of the third rectangle R3, my goal then to get any of these estimates is to add those areas up, R1 plus R2 plus R3. Now, as a side note, depending on the exact sort of person teaching the class or the exact resources that they want to use, there is some differences in notation. So this is something that you want to check with when you actually are doing this particular part. Sometimes they call, for example, R1, R2, R3 is specifically using the right endpoint. And then they might say like L1, L2, L3 would be if we were doing the left endpoint. And then they would do M1, M2, M3 for doing the midpoint. Like this is sometimes like some instructors will do that. Some will just call them all A, so A1, A2, A3 regardless. So for the sake of this particular video, I am just using R1, R2, R3 to be any of the areas, but know that sort of depending on your instructor, you might want to make sure that you know exactly the notation that they want you to use. Okay, so with that disclaimer aside, let's look at the right endpoint version. So the right endpoint version, right, our goal is, again, to get those areas, which means we need the width and we need the height. We know the width because we figured that out at the very beginning, right? So the width was the total width, 6, and we wanted 3 rectangles, so we divided it equally among the rectangles. The width is always 2. So that leaves the height. The height is the sort of question mark, right? But remember how we define these things, right? We had these upper right points, right? That's what made it the right endpoint, is we wanted those points to be the part where it hit the curve and to be the height of that rectangle. So really what we want to know then, when we want to know the height, is where these points are, because that represents the height of the corresponding rectangle to the left, right? So if we want to know what the rectangle's height is for this first one, we want to know what that dot's height is. So we use the points to get the height of the rectangle. But those points are points on the curve, right? And in particular, they're points on the function f of x at certain x values. So the height is just the y value of that point. And in particular, if we look at this one over here, for example, this is occurring at x value of 2. It's the height, so it's f of that value, f of 2, right? This one's f of 4, this one's f of 6. So our formula then, width times height of each rectangle, we want to put all these things together. So our approximate area is just the area of R1 plus area of R2 plus area of R3, right? The area of these 3 rectangles, which the area of a rectangle is just the width of that rectangle times the height of that rectangle. So width of R1 times height of R1 plus width of R2, height of R2, plus width of R3, height of R3. But now we know what these things are, right? So we know each of these widths are 2. So that 2, width of R1, times the height of R1, but that's occurring at f of 2, right? Over here, this f of 2. Then for the second one, again, the width is 2, but now the height is f of 4. It's this right here. And finally, the last one, right? Again, the width is 2, and the height is f of 6, this part right here. Okay, well, I can calculate those particular f's, right? So I can apply f to 2. This thing is just the function f of x equals x, or I can just look at the y values here. So that gets me that f of 2 is 2, f of 4 is 4, f of 6 is 6. So I can replace those, and then I can just calculate that out. And I get 24 as my estimate, okay? Now, if we think about it, right, this is a triangle. We can actually just straight up calculate what this is, right? So it's a height of 6, a base of 6, so it's 1/2, 6 times 6, so that's 18. The actual area is 18. We got an estimate of 24, which is arguably really big, right? Much bigger than 18, but that's maybe not surprising, right? Because we're including all of this extra space up here, right? This extra part, and this extra part. So it's not surprising that we get an overestimate. To be clear, it sort of looks like it should be an overestimate, that right endpoint should be an overestimate because of the function we're looking at, but there's no correlation between the type of approximation and whether or not it's an over or under, meaning it's not true that right endpoint approximations will always be overestimates. That's not true. So sometimes they'll be over, sometimes they'll be under. It depends on the function that you're looking at. Here, it is over. Okay, what about the left endpoint approximation? Well, same process, right? So again, we have that the left endpoints are so named because we're using those left dots, right? But those particular dots are also the height, which correspond to now, right, the same f of 2, f of 4, but they are the ones, they represent the height for the rectangle to the right, not the left, right? So this middle one is represented by this f of 2. The last one is represented, the height is represented by f of 4. And again, that first rectangle has a height of 0. So it's, I mean, you can write f of 0, which is, I mean, that is true. It just is also 0. Okay. So again, we go through the same process. So the approximate area is the area of R1 plus the area of R2 plus the area of R3, which is that same width times height for each of these things being added together. But in this case, right, it's now instead of doing f times f of 2, it's, instead of doing 2 times f of 2, it's 2, right, the width, times the f of for that height. But now we're using the left side, right? So we're using the x value on the left, which over here is 0. So this is now 2 times f of 0, 2 times f of 2, right? Because now this middle one, still width 2, but now has height f of 2. And the last one is 2, width times the height f of 4. So here I have 2 times f of 0, 2 times f of 2, 2 times f of 4, which when I plug that in, 2 times 0 plus 2 times 2 plus 2 times 4, that's going to be 12, right? Again, the actual area is 18, as we sort of figured out earlier, so this is an underestimate, which again shouldn't be terribly surprising because now, right, I have all of these rectangles are strictly inside and I have all of this other space that I'm not actually accounting for, right? So it's not surprising that I get some underestimate. And just like with the right endpoint, that's not always the case. It is not true that the left endpoint will always give you an underestimate. It could be under, it could be over. It always depends on the function. Here, it just happens to be an underestimate. So, midpoint approximation. Same deal that we did before, right? So again, we're using now the height that occurs at the middle x value, which again here, right, for the first one, that happens at 1. For the second one, it happens at 3. For the third one, it happens at 5. And so we're ending up with a sort of very close, so here we end up with that same height piece, f of 1, f2, f of 1, f of 3, f of 5, and we still have the same width, right, 2 in each case. So we're doing the exact same process again, right? So we have the approximate area, is that area of R1, area of R2, area of R3. That's the same width times height of each of these things. But now, again, the difference is we still have the same width, 2 times the height, but now it's f of 1, f of 3, f of 5. So we still have the same width, the 2 in front of each, but different heights for each of these, which again, when we actually calculate them out, gets us 2 times 1 plus 2 times 3 times plus 2 times 5, which gets us 18. And this one's a spot-on approximation, right? So this one is a perfect approximation, which again, geometrically maybe isn't too surprising because we can see like we overestimate some and we underestimate some, and so it sort of works its way out. Again, this is how it happens in this particular one, but not how it happens in general. Midpoint approximations can still be over or underestimates. They're not, in general, exactly right. Matter of fact, they're almost never exactly right. It just happens to work this way here. What is the key takeaway? Well, as sort of we saw by beating a dead horse here, the only difference between the different endpoint approximations is the x value that you choose or that you end up using to determine the height of the rectangles, right? Everything else about the formulas was the same. The width was always the same. The number of rectangles that we were adding up was the same. Everything else was the same. It was just the height that was different in each of these. So looking forward, as we sort of try to expand this into a more general formula, this tells us that we should sort of expect that the different formulas for the different endpoints, right, the left endpoint versus right endpoint versus midpoint, these formulas should look really similar because in some sense, lots about these different approximations are always the same. The only thing that's different is how we are choosing the x value for the height. So that's the only thing that should differ between the different formulas. Okay? All right, so at this point, before we move into the general formula, take a minute, take a break, let your brain rest and sort of decompress, chew through what we just did as our nice sort of concrete example. Moving forward, we're going to do a much less concrete example, trying to generalize this process. And as a result, it'll be very helpful to sort of have that concrete version in sort of the mental bank to keep drawing back upon. Okay, so we'll take a break here for a second, come back and move forward. All right, so welcome back. Hopefully your brain is a little less squishy after taking a break. So moving forward, our goal is to have a general formula for this process. And by general formula, what we really mean is that we want to generalize the one parameter that we sort of arbitrarily chose, meaning we picked a number out of a hat for the number of rectangles. And as it turns out, what we really want to do is sort of generalize that into n rectangles. So our goal moving forward is to develop some formula that represents what the approximation should be given some unknown, some n number of rectangles. Now, accounting for an unknown number of rectangles makes writing out that general formula a more technical process, and the resulting formula is more intimidating because we're going to need sort of some more machinery. And in particular, this is where we need our sigma notation. So moving forward, the formulas that we eventually get are going to be written using that sigma notation. And so it might sort of look a bit intimidating when we see the final result. But again, the real thing that you want to keep in mind for these different forms is that the only real difference between any of these approximations is the height, right? The x value that you choose or that we're going to be using to represent the height of each rectangle. So the pro here is that each of these three things, there's sort of not a lot to keep track of in terms of the differences between these three things. The downside is that they are going to look and be super similar, which means if you're just sort of trying to memorize the symbols, it is inevitable that you will sort of mix and match something somewhere and get something that isn't right. So hopefully, the idea here is that we're going to develop these formulas in a way that although they might look sort of long and technical, that they're broken up into pieces where the individual pieces should be something that you are sort of pretty aware of what it's supposed to represent as a concrete geometric idea. Okay, that's the hope going forward. All right, so remember the region that we're trying to estimate, right? Whatever that shape is. In our case, it was the triangle that we had, right? That thing, whatever it is, has a fixed width, right? In our case, with our three rectangle shape that was a triangle, that width was 6. So as we increase the number of rectangles, right, as we jam more rectangles in there that are all, right, all these rectangles are supposed to be the same width, that means that the width of each individual rectangle gets smaller and smaller, right? This is the idea is as we increase the number of rectangles, each rectangle gets thinner, okay? So if we start with some region in general, again, this is sort of trying to be a general formula. So if our region is spread across some interval a to b, again, with our concrete example, that was 0 to 6 was the interval that it was on. But if it's some a to b, if it's somewhere else, then the width of each of those n rectangles, however many we have, would be the total width, which is b minus a, right? Just like the concrete version was 6 minus 0, total width of 6. And then we divide that value by the number of rectangles that we want to use. So in our concrete example, we had 6 minus 0, so total width of 6. We wanted 3 rectangles. We divided by 3. That gave us a width of 2 for each of them. So in our general version, we are going from a to b. So our total length, right, our total, width of the region is b minus a. And we have n rectangles. So our width is, of each rectangle, means that we divide by n. So each individual one will be this b minus a over n, okay? So already, right, this is, I mean, we have one piece of one thing and we've already introduced 3 letters, right? But keep in mind that this is sort of one of those things where writing it down makes it look more sort of abstract than it is. All this is representing is the width of the rectangles when we have n rectangles and we're doing sort of a shape that is along that a to b interval. Now, by convention, again, our oh-so-good friend, delta x, shows up. So by convention, we usually use delta x to represent the width of these rectangles. So again, if we go back to our concrete right endpoint approximation here, right, we had, right, all of this stuff calculated out. At this step, this width of R1, width of R2, width of R3, those were each 2, which we got by doing that 6 minus 0, because this was on the interval 0 to 6. So 6 minus 0 divided by the number of rectangles, 3, which gave us those 2. So the width was always 2. But here, by convention, we're going to instead of writing width of for each rectangle, replace that with that delta x, okay? So here we will, in our formula, eventually end up with some delta x piece. But again, I really want to hammer home, because this is actually going to show up in a couple places. This delta x is nothing more than the width of a rectangle, once we figure out what that is for our n rectangles, okay? All right, so the other part of it then, right? So changing to n rectangles means that we have the width changing. We talked about that to get the delta x. The other part that changes is how do we represent these x values that are used to get each of the heights, right? So we know that what x value we choose between the different endpoint approximations, right? The right endpoint, left endpoint, midpoint, that is different between those. But even beyond that, how do we get, for even one of those, say the right endpoint, how do we decide, or how do we write down, when we don't know how many rectangles we have, what those things are? So in particular, we don't know exactly how many rectangles are going to be used, right? This is this n value, right? Some n number of these things, which means that sort of inherently we can't, like we are not able to write down concrete numbers that represent the x values that we want to use, right? We have to find some other way of sort of pulling out which x values we want to use to apply F2 to get the height of each of those rectangles. So to do that, again, keeping in mind that choosing the sort of choice of that x value is what differs between each of these endpoints, we're going to go through sort of a quick animation to show how this works in the right endpoint case, and then we'll use that as a way of sort of getting the other pieces, okay? So that's what's next. Recall that for our right endpoint calculation with 3 rectangles, we knew that each width was 2, and we got the height by evaluating f of 2, f of 4, and f of 6. But now we want to do it with n rectangles. This causes 2 problems: the width, which we now represent with delta x, and calculating what x value to use to determine each of the rectangle's height. So now we want to figure out which x values to use to get the heights. To do this, though, it helps to revisit how we originally figured out what x values we wanted to use when we only had the 3 rectangles. In the case of the 3 rectangles, we just looked at where the x values are, but that is less clear in the new version, and definitely not possible if we're truly using some unknown n number of rectangles. Let's see if we can deduce how the x values that we used were the right ones in the 3 rectangle case. Rather than looking at where the rectangles hit the graph of f of x and then tracing that down to find the x value, let's instead think about it from the bottom up. We know that the graph will need to hit the rectangle at the rectangle's right endpoint, since we're doing a right endpoint approximation. So that means we need to have the entire rectangle to the left of where it intersects the graph. In particular, the base of the rectangle is to the left of the x value that we used to find the height of that rectangle. So that means if we start at the first rectangle, we need to move over to the right exactly 1 rectangle width to find the x value that determines the height of that rectangle. So this gives us the first rectangle's x value for the height, the starting x value of our shape, which in this case is 0, plus the width of that first rectangle, delta x, which in this case is 2. But more importantly, we can observe the next rectangle is just 1 more rectangle width further to get the new x value. Similarly, we can do the same for the last rectangle. Using this notation then, we could write the area of our 3 rectangles version as follows. A equals delta x, f of 0 plus 1 delta x, plus delta x times f of 0 plus 2 delta x, plus delta x times f of 0 plus 3 delta x. Now, understandably, you wouldn't write it this way with 3 rectangles when you could just use the actual numbers. But this is exactly the way we will have to write out an equation for n rectangles. As you may suspect, however, since we'll have n rectangles, meaning that we won't know exactly how many of these terms to write, we will also need to use our sigma notation. So let's rewrite our current 3-rectangle version using that sigma notation to see a more condensed version. First, remember that the sigma notation iterates the index, meaning that we need to decide what value the index will start and end with. It makes sense, since we have 1 delta x, 2 delta x, and 3 delta x, to use an index that will start at 1 and end at 3. So let's try and write out the formula using k as the index, and starting at k at 1, and ending k at 3. Now, we need to put in the actual formula. Remember that this sigma notation is going to iterate the k for us, so really what we want is for the formula inside the sigma notation to be the formula for the area of a single rectangle, written so that as k iterates, we're adding up subsequent rectangle areas. So what we want is this. We can see here that the inside of the sigma notation has the two parts we're used to, the delta x in front, which is the width of each of the rectangles, and the f of 0 plus k delta x, which is the height. Here, notice that at the start, when k is 1, we get f of 0 plus 1 delta x. Then it iterates, meaning k goes up by 1, and adds to ultimately get delta x times f of 0 plus 1 delta x plus delta x times f of 0 plus 2 delta x plus delta x times f of 0 plus 3 delta x. And that's our original formula. So we've managed to write that original mess in a much more condensed form using sigma notation. Now, the good news is that we're actually basically done for the n rectangle case. If we look at what changes when we move to n rectangles, we can use the same notation, and really the only difference is that k will go from 1 to n instead of 1 to 3 for the 3-rectangle case. This is really actually because most of the changes are getting sort of secretly hidden by that delta x notation, so we'll address that in a moment. But for the n rectangle case, for the right endpoint approximation, we finally get the formula, the sum, k going from 1 to n, of delta x times f of 0 plus k delta x. Okay, so what about that delta x bit? Well, remember that delta x represents the width of a given rectangle. So we need to know, if we have n rectangles on some interval, like a to b, how wide is each rectangle? It's going to be the total width divided by how many pieces you're cutting it up into. So in particular, our delta x is really b minus a over n. So if we account for the delta x and assume that we want a formula for a generic interval a to b, we get the following formula for a right endpoint approximation. Again, it's helpful to remember what each piece of this formula is representing in a more concrete sense. The b minus a over n, the part up front, is the width of the rectangle for that width times height formula. And the f of a plus k times b minus a over n, that whole part, represents the height of the rectangle for that area formula. The a, in this case, is the starting x value of the region that we approximated. And the k times b minus a over n, that represents that we needed to move k rectangle widths over to find the new x value to use for the height. So even though the formula may look intimidating at first glance, if we can remember each piece by what it represents as a concrete geometric thing, it can help keep everything straight. At its simplest, we're just adding up the area of a bunch of rectangles, which means we need to multiply the width, delta x, and the height, f of a plus k delta x, of each rectangle to get the area, where we can calculate the delta x here to be b minus a over n. Further good news here is that the other formulas for left endpoint and midpoint are conceptually the same idea, just using different x values for the height of each rectangle, as we will see. Okay, so we saw how we do the right endpoint, right? We know how we get a formula for this right endpoint, but we still haven't talked about the left endpoint or the midpoint. So to get that, we actually are going to sort of look at the comparison between the two. So if we look at the right endpoint approximation versus the left endpoint approximation, well, we might notice that there's something sort of useful, some nice pattern happening here. So in particular, where these dots are appearing, right, these two middle dots are also appearing over here. And in particular, the left endpoint approximation is in some sense using the same rectangles, but moved to the right one spot. So in some sense, this this first rectangle here becomes the second rectangle over here. And likewise, the second rectangle over here becomes the third rectangle over there. So when we want to do the left endpoint approximation, we're sort of shifting the points, the height, right? The x values that we're using to get the height, we're shifting those over. So how does that affect the actual formulas? Well, if we look at the one that we already did, right, the right endpoint over here, so looking at maybe just this first part for a second, this is the normal thing we have. And in fact, if you actually just look at the formulas here, you'll notice that these formulas are literally exactly the same. So when I said that they should look really similar, really wasn't kidding. They look exactly the same because they are exactly the same. And this is because the difference isn't in the formulas, they are in the index, right? This is going from k equals 1 to n. This is going from k equals 0 to n minus 1. The reason, if you remember, this k going from 1 to n, this represented how many widths we had to move over, right? So for the first rectangle, we had to move one width over to get that first point, right? We started at the starting value, the a, which here was 0. We moved one width over, and then we went up to get that height, right? But for the left endpoint, we moved everything over. So instead of going to the right one, right, one width, we actually don't for the first one. We go to the right 0 widths for that first rectangle. So here we had to go one width over to get that first one. Here we had to go 0 widths over to get that first one. But remember when we were talking about this sigma notation, how it can be sort of a little misleading about how many of these things were adding up. We want to add up n pieces. So here, when we start from 1, we go to n. That gives us n. Here, when we go start at 0, we need to go to n minus 1 because we're counting 0. So this is still n things we are adding up, even though it ends at n minus 1. And for that sort of concrete version, the way you can think of it, is that here, right, we wanted this last height to be the very last value, right, this 6. So we went over, for that third rectangle, we went 1, 2, 3 widths over to get to that last piece. But over here, this height here for this last rectangle isn't the last value, it's 1 back. So we only wanted to go 1, 2 widths over. So we wanted to go 1 less width over, right? If we had 3 rectangles, we only wanted to go 2 widths over to get that last height, okay? Now, so the left endpoint is exactly the same formula, it's just changing that where the index is starting and ending. Now the midpoint is a little bit different because it's inherently using completely different looking x values, right? So here we're using 0, 2, and 4, possibly 6 for the right endpoint. Here we're using 1, 3, and 5, right? It's completely different. We have evens versus odds, right? But the midpoint, if we think about what the actual purpose was here, the midpoint goes exactly as it sounds, the middle of that rectangle, meaning that instead of going 0 widths for this first bit or 1 width over for the right endpoint, we actually want to go 1/2 endpoint in instead of a full. We want to go 1/2 width in instead of a full width. Now, we could do this in 2 different ways. One way we could do this is we could start at 0 widths and then add 1/2 width to get in. Or we could start at 1 width in and go back 1/2 width. So in some sense, you could look at this as starting with a left point approximation, which starts at 0, and going a half, right, adding a half a width. Or you could think of a right endpoint and going backward a half. By convention, we usually do it by using this left endpoint example. So this is why the left endpoint, the index parts, the k equals 0 to n minus 1, is going to be the same. But the difference is, instead of just having just k times that width, right, which is what we have over here. So this is adding the 0 widths to start with, and then we sort of iterate. We add 1 width, and then 2 widths, and then 3 widths, etc. Here, we're adding that many widths plus a half a width more. So that's what this plus 1/2 is. So in particular, the key here is that we end up with this plus 1/2 to the k, where the k is representing how many widths we're moving, right? So we start with 0 widths plus 1/2 a width in order to get this half part. And then when we increase it, we go 1 width plus another half, which would be this 1 width plus another half width to get to the next x value we use for the height, and so on, okay? So this is, again, very, very similar, right? Much of the formula is still the same. We still have this delta x out front, or this b minus a over n over here that is the width of the rectangle, right? All of those are always the same. The width is always the same. The only difference might be how we're counting, right? Whether we're starting at 0 and going to n minus 1, or going from 1 to n, and whether we're counting sort of whole widths, or if we want a half width for the midpoint version, okay? All right, so what did we do? So we sort of discussed how to estimate areas under generic curves using rectangles. In our case, we used this nice sort of rectangle situation where we could sort of have a actual shape we could actually calculate, right? So we used a triangle, but the same process is exactly the same for any kind of curve, including curvy curves. And in particular, we've had sort of 3 different versions of an approximation. We had the right endpoint approximation, which is this formula that we eventually got here, right? Which again is this width times f of starting place times how many widths you move over, where we start with 1 width over. We had the left endpoint approximation, same deal. In fact, the exact same formula all around, only now we're starting at k going from 0 to n minus 1 because we don't want to move that first width over for the first one. And then we used the midpoint, which was, again, just like the left endpoint, except we wanted to include another half of a width. So we have this k plus 1/2 here instead of just k, because k is the number of widths that we move, okay? All right, so that is that.